talking about the fancy lifestyle of rates of change. So rates of change, okay, also known as ROC. All right, we have, say we have this time versus distance, right? Time and distance. 2, 3, 4, 6, 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Okay. So you have 0, this is hours, 0.5, 1, 1.5, 2, 2.5, 3. Okay? And you have the distance that you travel, like 0, 52 it seems, 100, 120, 175. Make sure I'm not making a mistake here. And 250. Okay. So you have time and distance right there. That's time in hours. Distance, let's say. So let's call this in hours. Hours. Let's call this in kilometers. So what's the average speed at 3 hours? Then you just do change in distance over time. That's what you would do at this point. So you would just do d over t, which is 250 minus 0 over 3 minus 0 equals 250 over 3. That'd be the rate of change for the first 3 hours. So that would equal about 83.33 kilometers an hour. So we're measuring distance in kilometers in time in hours, right? So what's the average speed for the first 1.5 hours? Then I would just do the same thing, d over t. Right? You would do 120 minus 0 over 1.5 minus 0. That's average, right? Which equals about 80 kmh, 80 kilometers an hour. Right? So this is not too bad. It's kind of a reminder of your grade 9 days of what you used to do. How about the last 1.5 hours? So that would be between here and here. So you would actually do between here and here, right? Because from 1.5 to 3, the whole trip took 3 hours, right? So we would do change in d over change in t, so 250 minus 120 over 3 minus 1.5. So you get basically 130 over 1.5, which equals about 86.66 kilometers an hour. So that's what you get for the last 1.5 hours. A little bit of a trickier question, but nothing we can't handle. So basically, if you're given any function, this is not a hard concept. I'm sure you guys probably caught on what's going on right here. But really all that happened is that f of b minus f of a all over b minus a is the rate of change. That's all it is. You evaluate the function at b, you evaluate the function at a, and that's b minus a. So if you have a runner, so let's say, I guess I'll write the question up here, a runner, d in meters, right, over 60 seconds is given by this function f of t equals t plus 0.1 t squared. Okay, so you have t plus 0.1 t squared, let's say. Okay? What's the average speed for the 60 seconds? So just go f of 60 minus f of 0 over 60 minus 0. Okay? So we have now at this point in time is the value. If I put 60 in here, right, 60 plus 0.1 times 60 squared, right? Minus 0 all over 60. And we get about 7 meters per second. if you punch that in your calculator, 60 squared times 0.1, add that to 60, subtract 0. 60 minus 0 is indeed 60. You get your 7 meters per second. Okay. What's the average speed over the last 10 seconds? Then if the whole thing was 60 seconds, you would just evaluate f at 60 minus f at 50. 60 minus 50. Because it's for the last 10 seconds, essentially. That's all we're talking about in this question. So, then you can let some algebra to do, right? Just go erase this 7 right here. It's kind of blocking the way. The answer for this one was 7, by the way. So you'd have essentially 60 plus 0.1 times 60 squared minus 50, bracket that so you don't mess up the sign, plus 0.1 times 50 squared, all over 10. And 60 minus 50 is 10. You literally sub in 60 to the function, you sub in 50 to the function, and you evaluate it. You get essentially 12 meters per second if you were to work that out. And then the next question that we follow up with this note is for the last 1 second. So make sure you pause the video, get that down. For the last 1 second, all we do is sub in the values 60 and 59, right? Do f of 60 minus f of 59 all over 60 minus 59, which equals 60 plus 0.1 times 60 squared minus 59 plus 0.1 times 59 squared all over 1. So you get about 12.9 meters per second. That's the answer right there. So you can see that we're getting the interval between the times to be smaller as we go. Over the last millisecond. So millisecond, 0.001 of a second. Now we're introducing a new topic that are going full force on moving forward. But as you see right here, what we're going to do is do f of 60 minus f of 59.999 all over 60 minus 59.999, which equals about 12.99901 meters per second. Okay. That's all we're doing. Let's go over that. So we call instantaneous speed for the last second, essentially. So let's talk about the instantaneous, the definition of what that is instantaneous. What does that mean? What do we have to do? So what happens, the instantaneous rate of change at x equals a. What that is the limit as h approaches 0 of f of a plus h minus f of a all over a plus h minus a. So that's the limit as h approaches 0, f of a plus h minus f of a over h. Okay. Because what happens is that these a's cancel, right? The difference is a plus h. So as the distance between the 2 points, this h value gets smaller, right? You get this equation. This is the key right here. So you calculate the instantaneous speed at 60 seconds. What we do is the limit as h approaches 0 at f of 60 plus h minus f of 60, okay, all over h. And now we're going to get to this montage of solving, essentially. So we're going to do limit as h approaches 0 of 60 plus h plus 0.1 times 3600, right, plus h squared plus 120h minus 420. How do we get this value? It's essentially when you do the 60 plus h, all that squared. If I were to square the first term, I get 3600, square the last term, I get h squared, multiply the two together, you get 60h times 2, which is 120h, all of that. And then 420 is just the value at 60. All that's over h. So when you simplify that, okay, what you get is 13h plus 0.1h squared over h. You know you did this right if you're able to factor out the h. And how I got that is if you actually distributed this in, grouped all the h terms together, right, you'd be able to cancel it out. But now you can actually sub in, because what's going to happen is that you can go h 13 plus 0.1h squared, right? Well, h actually, all over h. So what happens is you put in 0 now for this, right? This goes away. You're left with 13 as your answer. So the instantaneous speed at that particular moment in time is 13. Obviously, there's a lot more algebra that I skipped over, but the main concept is covered. Okay, let's try another example. Let's find the instantaneous speed. What if we're at this function? F of x equals x squared plus 2x. We want to find the instantaneous at x equals 1. So what are we going to do? What we're going to do is do limit as h approaches 0, f of 1 plus h minus f of 1 all over h. So we're literally going to put 1 plus h in here. So that what that equals is 1 plus h squared plus 2, 1 plus h minus 1 plus 2, which is 2. 1 squared plus 2 should be 3 actually. So then that's all over h, right? Don't forget to write your limits. So when you simplify that, you should have 1 squared plus h squared plus 2h plus 2 plus 2h minus 3. Okay? All over h. You simplify that next, you get 4h plus h squared all over h. You can factor out h here for this. These h's cancel, right? And then what you have is you can, when you evaluate, when you sub in 0 in there, it's gone. So now you actually evaluate the limits, which limits actually 4. And then, so essentially, we could do this again for x equals 2, that's kind of monotonous. Let's do it for the value of a. Just any number. So the limit as h approaches 0 of f of a plus h minus f of a all over h, what you get is the limit as h approaches 0 of a plus h squared plus 2ah minus a squared plus 2a all over h. And you keep simplifying that algebraically. And you do the shortcut, or you can write a plus h twice. But I'm just going to skip to the bottom line. We get limit as h equal to 0 with 2ah equals 2h over h. You can factor out h so you get 2a plus 2. So what happens, I could have said x as well, right? Because it's x, you can say 2x plus 2. And our original function was x squared plus 2x, right? So this is going to introduce us to what the idea of a derivative is. We're going to learn about how to quickly go from here to here, essentially, with the next couple of videos. But this is a long way right now. It's called the definition of derivative. And that really sums up this lesson.